So at the beginning of the course, we developed or we derived the energies thinking classically. And I think we got something like minus 2 e to the fourth, where that's the electric charge. Pi squared. We had the mass of the hydrogen atom. We had n squared, and then we had h squared. So really this is 1 over h bar squared. Well, no, actually there's a factor of 2 there that we need to account for. Anyway, we should end up in the same place if we assume now that u is, right, we saw that u, let's give it some constant, u goes like r to the l plus 1, exponential of minus the square root of 2me over h bar squared r. It looks like that. So let's put this function into the Schrödinger equation and then find the value of the energy as we did before for other potentials. So in this case, it's minus h bar squared over 2m, 2 derivatives of the u function, plus h bar squared l times l plus 1 over 2m r squared, minus e squared over r times the u function. That's equal to the value of the energy times the u function. So we should get a value of the energy that's a function of L, given this assumption, and that should be related to the value of n that we got here. So we'll see a relationship between the n quantum number and the L quantum number. Okay, so let's, for simplicity, let's make this coefficient b. So b is, sorry, this is a negative here because e is negative, so that makes that positive. So let's call this minus 2me over h bar squared, square root b, so that we can simplify the calculations a little bit. So let's do the second derivative of u in r. That gives us, all right, we have 2 terms that depend on r, so we will use the chain rule. First we get a times l plus 1, r to the l minus 1, and then we have e to the minus br that just goes along for the ride. Then we have minus a b l plus 1, r to the l e to the minus br minus a times l plus 1, br to the l e to the minus br plus ab squared r to the l plus 1 e to the minus br. Okay, and that's equal to L times L plus 1 u over r squared minus 2b L plus 1 times u over r plus b squared times u. And so let's put this into the Schrödinger equation. So in the Schrödinger equation, which is this, let's see, we get minus h bar squared over 2m times L times L plus 1 over R squared minus 2b times L plus 1 over R plus b squared minus e squared over r. Sorry, let's see what I did here. Minus plus b squared minus e squared over r. Yes, but there's the term h squared, L times L plus 1 over 2mr squared, and that is equal to E. And so we can say that E is equal to, but in fact, this isn't the solution because we still have a B here, but we have h bar squared B. There's an E in here, B times L plus 1 over mass times R minus h bar squared B squared over 2m minus the e squared over r term, and that is equal to, okay, so let's resolve this b here. That's h bar squared times square root of 2me over h bar squared. That gives us 2me over 2h bar mr. I just pulled the h bar out of the square root. L plus 1 minus h bar squared times minus 2me over 2mh bar squared. That's this term, right? This is the b squared minus e squared over r, and this is equal to h bar minus 2me times L plus 1 over mr plus e minus e squared over r. Right, the e comes from here. We have minus e squared over r. And that's it. That's it. So we can conclude that we can cancel the e's on two sides, and so e squared over r is equal to h bar times the square root. Now we only have one energy term here over mr times L plus 1. And so we can solve for e. We have to square everything. E becomes minus e to the fourth, right, like we saw at the beginning, right here, e to the fourth. We have mass, and we have 2h bar squared, L plus 1 squared. So that's the n term that we saw there. Let's see if we can, here's the, so this is telling us that n is equal to L plus 1, and so L is n minus 1. There's a constraint there between the two quantum numbers. The fact that there's a 2 here just comes from the h bar squared, which is dividing, it's h over 2 pi. We square that, we end up with a 2 on the top. So these two match each other. So we got them. This might be a little surprising that we were able to get this from classical arguments, and here we got it from waves and the Schrödinger equation.